All right, today let's look at how to do a coupled thermomechanical problem inside LS-dyna. So what you have here is a structure that starts out with some temperature along the main beam and a higher temperature on one block and higher temperature on the other block. And you can sort of see this is a temperature plot where the beam goes through bending, but also goes through heat transfer through conduction across the length of the beam. You can also see the stress on the beam here based on essentially a thermomechanical problem. So as you know, like if you can change the stiffness of the material assigned to the beam based on temperature, right? We basically have a strongly coupled thermomechanical problem. And it is surprisingly easy to set up inside LS-dyna, even though the GUI doesn't have the functionality yet to directly do it. What we can do, as I've always done, is to use a series of template cards, which is going to essentially create this model for us. So I'm gonna do a quick demo, and I'll do a quick explanation. I didn't prepare a slide because there really isn't that much to talk about here, right? What I'm gonna do is I'm just gonna do a demo directly based on a prepared model that I already made. And then what I like to do, right in here is just to go over the basic thought process. And you sort of realize, right, the thermal part and the mechanical part are basically set up independently, but within the same solver, they essentially have a strongly coupled interaction that's embedded within the code, which is honestly one of the best thing I've ever seen. Like if you look at, a standard thermomechanical problem, right, you might have a transient thermal. Well, it won't let me. You might have a transient thermal with a transient structural, and you have to take them to system coupling to do a strongly coupled problem inside because those. But in this case, it's just so much easier within Dyna. Within Dyna, for a problem that look like this, all we have to do is just to set up a few sets and then a few keywords to combine it, and then we're good to go. Okay, so let's do this, right? Let's do this. So let's first of all, what we want to do here is like I mentioned in the previous video, right? There is no point in doing any kind of, insert command material type of deal because none of this would register with a thermal problem inside the workbench on the Dyna. It's just not set up yet. So what we want to do, right? Just as I did with the previous video, right? Let's just go ahead and get started and setting up a few sets. These sets are basically the things that we're gonna call with our command snippets or with our keywords later. Okay, call this contact 1, contact 2, contact 3, contact 4. That's the 4 different contact pair which we're gonna be using to create our contact cards. Okay, and then because I already know what I want to use them for, I'm just gonna call this 8001, 8002, 8003, and 8004. Okay, that's my 4 contacts segments, which I'm gonna use. I'm gonna put them into a thermomechanical contact pair in a bit. Okay, that's the first thing. Second thing is that we need to define a couple of these bodies. I'm gonna call this the block. I'm gonna call this the beam. And I'm gonna call this the base. Okay, now with these 3 things, right? What happens with them is that the thermal boundary condition, like initial temperature, for example, that you need to assign to the individual bodies, these are always going to be a nodal set. So what you want to do here is to generate a nodal set for each of these. I don't have any nodes here because I haven't meshed it yet. So let's go ahead and mesh this. Real simple. Right. And then I now have these nodal sets. Now these nodal sets are where we're gonna use for the sets that we're calling. Now, interestingly enough, right? Like you want to know how easy it is to set up a thermal problem in Dyna, right? It's so ridiculously easy. If you just create templates. So what I can do, I'm just gonna do it just to show you, right? It's if once you have a code template, right, it becomes a lot easier to do these things, right? I'm just gonna do it. So what I'm gonna do here is that I'll just copy paste stuff over, right? So this is my contact pair. Notice 8001, 8002, 8003, 8004 correspond to 1, 2, 3, 4, right? Next one, I'm gonna use this is my implicit control cards. This is my implicit control card because because uh, it is essentially a setting. I've actually gone over this in one of my other video about doing implicit LS-dyna, right? Now you could copy this template and change this number based on the nature of the problem, but this template goes in here, right? And then you just have to change these parameters. Very easy to do. Next one, we're gonna do our thermal control card. This is what defines the thermal solver behavior. This is what defines the structure solver behavior. Okay. Initial temperature. Now the initial temperature is important because each of these body needs to be assigned initial temperature so that you have a thermal flux going from high to low, right? That thermal flux is needed for the initial temperature setting. So this 9001, 9002, 9003 are the initial temperature for these three bodies, which defines the thermal flux directions that we wanted to do, right? And then of course, what we want to do right here is that we want to set up a boundary condition where this is fixed and this is fixed, just so that and then I'm just gonna create a fixed support. This become my fixed support and then I want to create a remote point, and this is gonna be my remote point. Now this remote point, I want to make sure it's located right in the center of that wall. And then of course in here, what I wanted to do is to generate a boundary condition to move that remote point down by 30 millimeters over 1,000 seconds, right? So I'm gonna move that block down by 1,000 seconds. Now this node number right here, right, is not gonna be 23214. So what you do here is use the common script I've been using almost every day now. Is use this little quick script to find the actual node ID, which is actually 3214 because of the nature of the mesh. So you see how this remote point has an ID of 3214. That 3214 becomes the node ID of that remote point, which is actually converted to a CNRB, a node number which is converted to a CNRB. So by having a boundary condition on the 3214, right, in the negative x directions, in this directions, we're going to press the block against the plate, against the beam. Okay, and then lastly, but not least, we need to generate a keyword. Oh, sorry, I actually didn't need to do that. And lastly, but not least, we need to generate a thermal keyword, thermal part. Now, the reason this is necessary, right? You see, I have three parts in here: one, part two, part three, correspond to these three parts. So this is the base, this is the cube, and this is the beam, right? Now, the reason this is necessary is I'm just gonna go ahead and write out a input file. I'm gonna call this. I'm gonna save this to the download page. And then I'm going to go to the download page and open it in my editor, right? So you see how in this case I have this mat part section mat ID thing, right? These things are no longer needed because I don't have a TMID in my part. You see this TMID doesn't exist, and I went over this in the thermal part of the video, which is the first part of this video. So what you wanted to do here is that you see the first one is base, second one is cube, third one is beam. So we want to modify our template, and this template can be expanded. You can add more parts, right? Basically, each of these parts are my cube, beam, and well, actually, let me double check real quick. So it's gonna be my base, cube, and beam. Base, cube, and beam. Okay, so this is gonna be my base. This is gonna be my cube, and this is gonna be my beam. And you see, they all. In this case, I made it simple, right? They all have the same section, and they all have the same mat elastic as their structural material. But for the thermal material, right, I'm assigning them all to the same thermal isotropic material, which just has a conduction and a heat capacity, which is defined right here. I'm just making it simple. You obviously they can have very different thermal material models, right? They can have temperature dependent material models. You can add in here, and then for each of these, I'm gonna add a thermal expansion to each of these because it's a mechanical problem. As the heat is added to the material, you're gonna have a thermal expansion on this. And this is what we're doing, right? So basically, this call replaces the part card that's going to be written now, and all you have to do is to go here and write back into the test. And in the actual text file, we're going to actually, what just happened? Oh, I know what happened. I'm sorry about that. I need to do this. Obviously, we have to disable the default control cards, the default database cards, and then we're gonna call this the contact. I'm gonna call this the implicit FEA control. And call this the implicit thermal control. And we're gonna call this the initial temp. We're gonna call this the BC, and we're gonna call this the thermal parts. And obviously, by turning off the control cards and database cards, I need to have a control card. I need to have this is my default control and database templates. If you've seen my video before, I have these templates that I've created for default control and default database. Right, this is my default database. This is my default control. So all I'm doing right here is I'm gonna copy over my default control cards, which I've already modified a little bit so it doesn't have what I don't need, right? And then I have my I always do this, so let's change this to control, and then change this to database, and then the default database card, which is these, right? The most important one are the D3 plot, right? So it's all in here. This basically defines the most common one. I don't really need all of these, but in this case, I just go ahead and have kept them. It doesn't really add a lot of file sizes. It doesn't really matter in this case. And of course, we want to change our remote point to rigid, and it's going to be converted rigid anyway, but let's just go ahead for best practice. Go ahead and do that. And this model is ready to go, right? I set up in 10 minutes for a model like this. By using template, right? The challenging thing about a thermomechanical problem is that you actually have to control the solver behavior between the implicit structural side and the thermal side, right? For example, you see this delta T, this T0, right? You need to make sure they have matching time steps, right? So if you make one solver control have a lot smaller time step than the other, it's gonna create problems, right? It's also related to the way the time stepping works, right? So for example, in an implicit analysis, you have to control how large of a step you take, all right? There needs to be sort of a consistency between the mechanical side and the thermal side. And you want to make sure it's not doing weird things. So that takes a little bit trial and error to make sure you get it done right. Now, obviously, to really get the problem right, you have to adjust these solver settings, right? Which are in these most important card, these two cards. You want to make sure you don't have a situation in which you have divergence, right? In which you have really weird. There are for example, in the thermal side, there are settings in which it checks your maximum temperature change per time step to make sure it's not so you don't have a single step you take that's generating a really big temperature change. They are trying to prevent that, right? There is also a minimum time step, a maximum time step you can choose, so you don't take too big of a step or too small of a step. Too small step means you just basically the solver stops, right? On the structural side, you can actually switch the explicit to get it to get past a very difficult time step. So there's a lot more going on, and there are really good resources out there that let you sort of deep dive into the thermal analysis. I think his name is R. Shapiro, has a lot of really good resources that I've seen. I'm certainly gonna go deeper into it myself, right? But this overall is the setup, right? So if you look at everything I did, this is the thermal contact pair, right? This is my conduction, this is my minimum maximum gap, and then that's essentially a thermal mechanical contact pair. It's an automatic surface-to-surface contact, which is essentially like a frictional contact. That's also a thermal contact. So that contact pair, this single contact card, can transmit heat through conduction. It can also act like a mechanical contact, right? So it's a really awesome feature they've created. These are the powerful, most important things you want to fine tune to get the problem to solve correctly. You have your initial temperature, you have your motion of the actual displacement of the pluggers applying the deflections. You have your thermal part, which replaces the part that's written out by default by the solver, and you have your database card and your control cards, and together they serve everything. And then this is the solution that you're looking at, right? So you have a very clean overall solution here. That's going to be a thermomechanical problem. And right here is how you do a thermomechanically co-simulation inside LS-dyna. Thank you.